All right, sticking with exponential equations, let's do some examples that involve the natural exponential function. So this is e to the power 2x plus 5 equals 12. Okay, so there's one exponential expression in this, and it's the first term right there. Plus 5 equals 12. Hey, I might as well just combine those together. Let's do that. Let's subtract the 5 first. That is easy to do. Now e to the power 2x equals 7. Okay, this is a base e. That's not base e, but I should be able to handle this somehow. In the previous example, I showed how you could just do a log of both sides. In this case, I'm going to choose specifically the natural logarithm. I'm going to do the natural log of both sides, because the natural log is going to cancel out the base e exponential function. These are both base e, natural exponential, natural log. Their bases are the same, so this is like, f composed with f inverse here, okay? They're going to cancel out, and I'm just going to get 2x by itself on the left side. The right side is still the natural log of 7. So now my x is just natural log of 7 divided by 2, okay? And this strategy of using a logarithm to cancel out an exponential is a very fundamental strategy that you can use to solve lots of different equations. So like even if it was like 7 to the power x plus 5 equals 8, you can do log base 7 of 7 to the power x plus 5 equals log base 7 of 8. And then this will cancel out, and you'll get x plus 5 equals log base 7 of 8. And you can just subtract the 5 and get x is log base 7 of 8 minus 5. And that's some number. And this is the exact form to write that number, because log base 7 of 8 is going to be some irrational value. Okay, 8 is not a clean power of 7, so that's just going to be irrational. Okay, so now, moving on, let's look at another example involving the natural exponential. For this one, we're going to do e to the power 2x plus e to the x equals 2. All right, this deserves a little bit of discussion. Now there's two exponential expressions added together. Now, if you add exponential expressions together, you can't combine them. There's no property that would allow us to combine those. And if we do the natural log of both sides, like we did in the previous example, that's a valid step, but now we cannot split up this logarithm, so we cannot cancel inverses. Okay, we would only be able to cancel these inverses if we could split the log and do the log of each term individually. But since it's the log of the sum of exponential functions, that is not, we can't just cancel the inverses there. So actually this step is not a useful step any longer. Not as a first step, at least. We might do something like that later on, but our first step in this problem has to be something completely different. And this is something that kind of comes out of nowhere, and you might not think to do this unless you've seen examples like it before, which is why I'm showing you one. If you look at e to the power 2x, you can use the power rule for exponents to rewrite that as e to the x quantity squared. And then let's subtract 2 from both sides and get it equal to 0. Okay, I'm specifically putting it in that format, and I'm going to put the parentheses around e to the x as well, even though I don't need to. Just so that you can look at that, stare at that for a second, and think, have I ever seen a strategy that would help me solve something like that? Do you recognize what's going on here? That's right. This is in quadratic form. So since this was specifically e to the 2x, and this was e to the 1x, this is e to the x squared, right? And this was e to the x to the power 1, and then we have a constant term. This is basically a quadratic equation, but with u equals e to the x. Let's switch to another color. I'm going to switch to purple. Let u equal e to the x. So now we have u squared plus u minus 2 equals 0. Okay? So now what we can do is solve this for u. Okay? This is a quadratic equation. This one happens to factor really nice and easily. This factors as u plus 2 times u minus 1. And then each of these is going to give us a solution. If u plus 2 equals 0, u equals -2. And if u minus 1 equals 0, u equals +1. So then, having solved for u, we're not done. Okay, I'm switching back to black. Now we need to undo the substitution we did. We said u was e to the x, right? So having solved for u, now we're going to replace the u's with e to the x again. And we get two equations. E to the x equals -2, or e to the x equals 1. And we have to solve both of these. And we can solve with logarithms. X is going to be the natural log of -2, or x is the natural log of 1. Now the natural log of -2 is actually undefined. Okay? So in that situation, on this side, this does not give us any solutions. Okay? You could have figured that out right away, since e to the x equals -2 is going to have no solutions. The e to the x function only gives us positive numbers as outputs, because its range is 0 to infinity. So it's not going to be possible for that to ever equal a negative number. So that possibility we can ignore. We have to consider this possibility, so you've got to write this down, all right? But then it doesn't actually give us any answers. However, over here, if e to the x equals 1, if x is the natural log of 1, x would be, that equals 0. And so this does have one solution at x equals 0, and you can double check it. E to the power 2 times 0 plus e to the power 0, this is actually going to be 1 plus 1, and 1 plus 1 equals 2. So, so there we go. That's how you can solve something with u substitution.